Okay. So, like, what do you want to repeat? What do you want me to repeat? Okay. Uh, can you speak? Let me check my audio is fine. Can you try speaking? Is my voice audible?
Hello, 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 mic
Audio
test.
issue. Check. Yeah. Can someone now try audio?
Hello, mic test. Hello, mic test. Hello, mic test. Hello,
Try now.
hello,
Yeah, yeah. Now it's audible.
yeah,
Yeah, there
hello.
was. Yeah, yeah. Now am I audible? Yeah, you are audible. I am audible, right?
Yes, you are also audible.
Oh, understood. So, what I have to start from?
From the beginning, please, if you can.
Okay. So, I was explaining about how we can use this platform IO tool to compile your Arduino code locally and run this, right?
Right, how did you get this far? Could you show from the blank screen, please, if possible?
So, this is the VS Code editor. You can install it from the VS Code's website. So there is a VS Code extension for WalkMe, which you can install from extensions in VS Code after installing VS Code. Then Platform IO is a tool which you can install from this command line. So this is the code command line, which is written in Python basically. So you can install installations. Yeah, you can install it with this one or the pip or any package manager that we have. So if you have platform Python installed, if you have Python installed, you can refer this and install platform IO. So platform IO can set up a project like this for you using the platform init command, and then you can add this source. You can add the main CTP file, which will be uh, where we write the code. So this is a different way of writing code rather from the traditional Arduino IDE. This platform I work has different tools for compiling, running, and if you have a real code, you can also push your code to the code using the platform code. Okay,
Do we need Python for this?
your system needs Python for that. Okay,
So we need to install Python first
yeah,
and then platform IO.
yes.
And then what command we are supposed to run on the platform IO?
that we have to, but we can refer in this platform I was getting started with. The different commands will be listed here. You can check what are the different commands that you have. So I used a similar command to this to initialize a project. That will initialize the recruit project. Okay. And this basically what I have said is already present here in this docs. In this quick start guide, whatever I have it, this is what I did. Right? The data.c file and did the remaining things. And this will target upload will do this thing, right? So this is for uploading it to the board if you have, but you can do this run only to build this thing. So building will create the binaries and put it inside this particular folder, which we have linked in the walkme.toml file for the configuration of simulation that in walkme in this VS Code. Okay.
So we have opened this platform IO test in VS Code, this folder,
Yeah,
and everything
this is it.
inside platform IO test is already ready. Sorry, some clowns are
Yeah,
bursting crackers outside. I'm sorry about that. Yeah,
yeah,
so platform IO.test is a folder and its files will be ready after we do everything you previously described.
yeah,
So sorry about that. And then you said there's an extension in VS Code for WalkV.
yeah. So that if you only install that, you can see this diagram.json and this simulator when you run this. So the free version of what we come, you cannot edit the diagram in this offline, but you can see that like you cannot edit using this drag and drop, but you can always edit the diagram.json file, right? You can just open it, open with text editor, which will open the diagram.json as a text file. You see, uh, I can edit the diagram by editing the JSON file also. I can edit the attributes directly. And so, for example, if I want to connect this to 12, see, the diagram is connected to 12. You can change the diagram by actually modifying this also. So, if I want to add another LED, you could always copy this. If you know how JSON format works, you can add an LED, and now I'm just pushing it to size there, and you can add a connection. So these are LED1 connections, right? So you can add a similar type of connections with LED2 also. LED2 cathode can be present in ground, this way, and anode can be present in the, yeah, that is connected to 30, but not in a way, right?
We could design the diagram entirely on the free online walkway and then copy
Yeah,
paste that JSON thing over here. Is that
yeah,
possible?
that would be easier. You can do that. Okay. Essentially, what I am trying to say is, uh, this is the barebone of this diagram. This diagram is totally represented by this JSON, which are certain attributes. You can play around by editing this diagram. Basically, you can see whenever I update the diagram, the JSON changes, and you can do the things by doing this. So if I have to change these things, you can always do that. Okay. So, if, like the advantage of directly editing JSON is you can create multiple copies like this easily. You can put LED3 and LED4, and then just add up some numbers like this. See, we can quickly create copies easily. So that's the advantage of directly editing the JSON. Now we can stop this. So now let's start with how we can code using this part, AVR, right? So we did the code using Arduino. So basically Arduino functions are defined in Arduino.h. Arduino IDE won't require you to write this include statement because it includes it by itself. Now, if you are using a main.cpp and using this kind of things, platform IO, you need to specify this. Now, for this one, AVR, all the IO functions and the registers definitions are defined in AVR.IO.h. So that's why we have included that. So now we want to look at what are the different ports that are available here. Yeah.
Yeah, just wanted to ask that include Arduino.h, is it available inside the platform IO include folder? Is that how it is?
No, platform IO actually has a common folder addresses for their data. So it has a data folder. So usually when you install Arduino, all the header files and things will be present in uh, certain app folder. So there will be a folder for each app, right? If you in Windows, if you see these program files, there will be a folder for each apps. There it will store these things. So similarly, Platform IO also uses certain common directory for its files. So this folder is for creating your own includes, not from the Arduino. Okay, if you want to create your own header file, you can put it there. That's what. And uh, if you need to include any libraries, you can just put the library folders here. Those will be included. Okay. Basic Arduino and AVR, these libraries will be available from its catch folder itself. So that platform I hope
So
will get that.
that is what we are calling in the include Arduino H here.
Yeah,
And similarly in the include AVR also, we are doing the same thing.
yeah. Okay. So now uh, we want to know about the different registers that are present in the uh, IO configuration, right? So to configure a pin, what you have to do? So there are certain registers there, UDXN, port XN, and pin XN. So these are the registers that are there. So there are different ports present in this. Uh, this is PD 123. These are the D port, and PC. These are the C port, and PP are the D port. So there are different GPIO ports available in this uh, Atmega 328P, which is our uh, this one. So this microcontroller chip that is present here is the Atmega 328P in Arduino U. That's what we are seeing here. It might be not the same shape, but the same thing. Okay. So the idea is to configure this pins, we need to set the pins here. So DDXN bit. So DDX. So there are two names that you will see here: names of the registers and names of a particular bit in the register. So every bit in this registers of this particular chip has a name, and also every registers will have. So DDRX refers to data direction register of port X. Port can be A, B, C, or D. And similarly, this is the data direction in of that in that particular register. Okay. So this gives us some context about that. So DDXN, port XN. So DDX will be, so okay, port XN is the uh, nth bit of the particular port. So this is a bit. That's why you can see this value 0 7. This is also a bit, DDXN, data direction uh, bit. And then this one, PUD, MCU. PUD is push up or pull down, like push up or down. That's what it refers to. Okay. So in this case, you can see now don't worry about this input thing. If you see this data direction is 0, the mode is input. And if the data direction is 1, the mode is output. So how will we set the input or output mode? Using this one. And what does this mean? If this is 0, uh, it means it is uh, yeah. So let's check. Don't worry about this input configuration. Now just worry about this output. When in output configuration, this doesn't matter. So now we are actually dealing with the output. If this is 0, this means the output is low. And if this is 1, the output is high. So in output mode, the port register, port pin, like this particular bit value will change the state of the pin. Okay. So now uh, these are certain C programs that they have given to operate on this. So what is this port pin? These are just masks that they are actually doing here. So let's see this. So these are the register names, and these are the value you are setting to that particular register, right? Okay. Now let's implement something like this for the. So how do we set up? So we saw that. So if you want to modify a particular configuration, you have to uh, update the register, right? Which is DD. So let's see first what is this pin. So do we know what is this pin is? So to know that, we have to open another Arduino data sheet. So here in this data sheet, you can actually um, yeah, yeah, find the port numbers. So D13 is actually PB5. Okay, that port numbers we can find from here. So PB0 to PB5 is in A to B30. And this is PD0 to PD7, 8 bits, okay, continuously. So these are the pins that we will be working with usually, right? So to do that, PDB 5. So we have to mask the fifth character. So I have to set that to 1, which is uh, DD. The number is 5. So what is this number? This value basically expands to 5. Okay. This means you can mask that fifth character. And that's basically the idea. So okay. So data direction register. So we can update. So what this value basically expands to, the register's address in some sense. So this registers up, we are updating that register's address to this value. So these are actually defined in there. So this is basically doing this pin mode is equal to 30. And now what about this? You want to write something what register we have to update? We have to update port B, this register. That register we have to update, which is port B is equal to, we have to set that particular value, which is 1 times EB 5. We have to set that. Right. So that's basically setting that particular thing. So now this will make this on. So if you do PIO run, uh, here this, you can see pin 13 is now turned on. That's what this code does. Right. Now let's, uh,
Excuse me.
yeah.
Maybe you covered this before and I missed it. Where exactly did the compilation and the execution of this whole process take place right now?
So when I run PIO run this command, it compiles. Okay, and the things will, it will create these two files, and the simulation happens with the simulator, which we have to configure using this file walkme.2ml. We have to set the paths to that files that are generated. After this configuration is there, the simulator will be able to run that. You can run it from here in the simulation. Compilation will create the binaries. Simulation you can start from this, which will actually uh, get these binaries and run this. Okay, so you just have to compile after
So
editing.
the PIO run command will do the
Ah,
compilation for us.
yeah.
And
So now
who
if
is
we want
creating
to,
the walkaway.toml? Who is creating that, please?
we have to create. We have to like uh, assign these ELF and EX, these two paths to here. You can see that path, right? You can just copy related path and paste it. They have to define those variables here in this walkie.ml file. This is like settings.
So we can just make that file
Ah,
walkaway.toml in our folder, simply
yeah,
just like that.
yeah. And this is the format. There should be this key, and these are values, kind of that.
So the process for making that platform io.ini is also the same.
No, that is created by the command itself. When you run PIO init, all these folders and this platform.ino file will be created. This
Sorry,
is
which command?
first you have to run PIO init. So I ran this command, which I give configured the board ID and the framework that I'm going to use.
So that
This
is the
command
first
will,
thing to do, I
yeah,
guess. Okay.
yeah, I explained that also. Maybe you might have missed since the audio is not clear. You can refer this quick start. This actually has all those things. See there, initializing the project. You can list the boards using PIO boards, and it will list the board names, and using that board names you can do the configuration and stuff. Okay, now let's do this. So now if you want to turn on this LED also, which is connected in 12, which is PV4, what we have to do? We have to set the DD4 also. Now this is just setting pin mode 13 output and pin mode 14 output. Sorry, 12 output. Setting those two as output in the same line. That's what this does. And to turn on both things, you can just use bit masking to create that particular corresponding bit mask. 3D4. Now, if you compile this using PIO run, oops, uh, the determinant, sorry, yeah. So now you can see both entities are blinking. Right?
Excuse me.
Uh,
Seems like DDRB is some settings register, and in that we
DDR
have,
is data direction register for the port B, which data direction means input or output. If
so
that
depending
particular
on,
bit is set, if a particular bit is set, that is input. So we saw in this, right? If this bit is set, which means it is output. If this bit is not set, which means that is input. So by default, all bits are will be in input mode if you set it to 0. So by turning on only these pins, we are setting that two pins to output, right?
okay, thank you.
And by setting turning on this port action, we are making it high or low according to this. So now we have created this. So to make this low, what we should do? How do we make this low? We make this low using resetting. So how do you reset pins? You add with the, so this is basically setting everything, right? And just turning on everything. Instead of that, you can also use this notation, which is like setting that particular bits. So what does this mean in the area? It is called setting the bits. So when you assign, what happens? Basically, what will be the value produced by this? Any idea?
There will be a 1 in the position of
Yeah,
PV5 and a 1 in the position of PV4, everything else 0.
yeah.
So all
Everything
other
else is
30
zero.
values will be 0. This is a
Yeah.
32-bit, right? Register, port B.
Eight, 8 bit, 8 bit registers.
Okay, so two of them are 32, the other six
So
are
there will
0.
be 8 bits, and these bits will be only these bits will be on, and other 8 bits will be off. But when you do this, what happens is it doesn't change the other bits, but only makes these two bits as one. Doing an OR will not affect the previous state, but will the state of the other bits, but only will affect these bits. If the other pins are turned or on or off before, it will stay the same. But these pins will be surely turned on. That's what setting the bits mean. And we do that using ORing with the mask. And this is the mask. This is what we call the mask. And to reset, what we do is yes, we do and with the uh, negation of the mask, which is this. So ending with the negation of the mask.
Excuse me, this notation is just similar to the plus equal to we used to do in the.
Yeah, this is R equal to and this is and equal to. Which is same as doing this. Okay. And this is also similar. That's the idea. So
Okay.
get the mask, we negate it and we AND it to reset the bits. Now only one thing missing from this is the delay. So creating delay is a complex task. So we'll be using another function from this AVR library to create a simple delay. Delay.fetch. So there is this function called delay ms. This one. which is millisecond. Yours is microsecond. Okay. So this delay was we can give the number of milliseconds to create the delay. See, you can create for you can see the blinking LED code, right? So this is by directly manipulating the registers. You don't have to. So actually, I am turning on both the LEDs in a single state. So if I have to do that using Arduino, I have to do a two digital arrays. And since these are in the same ports, I am doing it the same statement. So if I want to also use LED from here, I still need to add another statement corresponding to that port. Here this is port D, right? So port D6, and then we have to configure that accordingly. So you need to know the registers of the pin mappings. That's what. So more you do it, say, more you need to refer to the data sheets and the mappings like this. So if you want to add LED here, what will be what should be just things right now. LED put 6. Okay.
I think you showed us that those will be part of the port A list of pins.
Sorry.
No, if I remember, you showed us that those are from the port A list of pins, right?
Put D PD PD0 to PD7. PA is these are PC and these are PD bits. Although the first 7 pins correspond to the same number if you see in the port D. So this is basically the 8 bits of port D, and this is the 5 bits of port B. That's more. Right. And the built-in LED is connected to BB5, which is basically 13. So if you edit that, then you can see the built-in LEDs also. So now with this, if you want to do this is PD6. So you have to set the data direction register for the port D, and here you have to set 6. Then here you have to add PD6, and you have to do this also. And with the negation of this. Right, and okay. But this has been going to, yeah, fine. Now to start working, we can I can see all these things are, yeah, indoors. So there is another thing that we can do this other way also. So here we are setting and resetting the bits basically. But what alternately we can do is also toggle the bits. So toggling, you can basically do XORing with a particular uh, mask. So XORing with the particular mask. So this is the XOR operator, which XORs the bits. So XORing with the particular mask will toggle the bits. If it is on, it will turn on. If it is off, it will turn off. So we don't need to separate uh, on and off loops. We can just go with this. That's the idea. Here and you can see this happens. So change the delay. Now we can see. Okay. So instead of toggling and it's like on and off, we can just toggle the bits after every 500 ml something instance. Okay. So we're able to understand toggling.
Sorry. This is just that in when doing the XOR, never mind, I'll just stop.
Sorry. Sorry, what was your question? What was your question? Anyone else? Or do you have any doubts in this? Okay. So we'll see how we can also take inputs from this. Right? Uh, yeah, this one. So to configure a push button in pull-up mode, what we have to do? This configuration. We have to set this one to 0. So this is setting it in input mode, and when this port in will be turned on when we pull up, right? So sorry, this is actually uh, yeah, this is pull up. So we have to set this to 0. Okay. So setting this to 1 will not make it pull up. So this is for when you are going to take input from a sensor. This is for when you are connecting a push button like that. Okay. So let's connect a push button and try this with this. So we should here change the diagram. Let's remove bounds for now. Let it be a simple button and I'll connect it to this. And this will be connected to ground. Okay. Now we are connected it to PD4. So we have to configure that, right? So here what we have to configure, this can remain the same because since it is in input mode, the data direction register is 0. So that we don't have to change. We have to change this to 1, right? We have to enable that input exceptions. So we should do that one. So here we can turn that on. Port, uh, sorry, port D. So to turn that on, we can do a R equal to also 1 BD4. 4, right? So which enable that uh, pin for input. To do a pull-up, we have to make this 0. I think by default it is 0, so we don't have to change that register, right? So now let the first two LEDs, these two things, do this in a delay. We want to do this, and okay, since we are going to do something simultaneously, using delay might not be a good way, right? Mm, Let's okay. So correspond. Okay, let's remove this delay for now. We just get rid of that for now. Let's focus on this one, this part. So we are going to use PD4 as a input and PD6 is the output. So it will be just a minute. So what do you have to do? So how do you read values? Any idea? So this is writing into a particular port, right? You can assign or set, reset, and toggle. How do you get a particular bit value from a number? If you want to get the input value, what will you do? Any idea? To get the nth bit, what you have to do is left shift this particular value to certain number of uh, bits that you want to get. Here is a PDs 4, right? Now, if you add this number with the 1 and also 1. So what is this doing? It's bringing the fourth bit to the first position, the LSB. That's what the shift operation is doing, right? So this register has certain value, and you are bringing the fourth bit to the LSB using the shift operation. And then you are adding with the 0 or 1, like 1. So if this LSB is 0, all this adding will make everything 0. If this LSB is 1, adding will make it 1. So this will give us whether that particular pin is set or unset. So this is basically reading a particular bit. Okay. So if this is turned on, we can. But since we are using pull-up mode, we should be checking it is turned off to ensure the pull-up logic. So if this is not 1, which means the button is pressed, you have to turn on. Uh, let's see. Let's do this. You have to turn on this, or else you have to turn off this. Okay. So let's run this. Now let's press this button. Now start this right here. Oops. So, uh, second. configuration tools. No? We have to make, yeah, we haven't made this one. Okay, we have made that. This is 0 line. Let's see this one. Okay, this will be by default set as this one be. So you don't have to set this value. Okay, okay. So this since we are reading this, we shouldn't be setting this ourselves. Oh, okay. This is four. This is 4 and 5 for this one. So, reading the pin. Oh, okay. So we have to read the value through the PIN-X register. So the PIN-X register will have the readings, not the port that is for going the output. So our value this will give us the set the direction. Seems reading is quite complicated. I'll check this and we'll do this the next class. Okay. For now, let's go on to the reading part of this. So I hope this writing part is fine. Uh, with that we'll move on to this next one, which is interrupt. So these are the interrupt pins that we'll be having: timer interrupt, uh, pin interrupts, external interrupt. External interrupts are caused by the inputs from the pins, and timer interrupts are caused by timers. So there are three timers in this um, Atmega thing: timer 0, timer 1, and timer 2. So timer 0 is a 8-bit timer, and these two are one is 16-bit and timer 2 is also 8-bit, but it has some asynchronous operation functionality also. So there are different functionalities associated with the different timers. So if we see, so there are certain registers that are present in this timer also. For example, OCRA, OCRNB registers. These two registers are there. TCCRNA and TCCRNB register. So these two are configuration registers. So timer control configuration registers, and these are output compare registers. So we'll see what output compare is, and then TCNT is the counter. So this will have the counter's value in it, and then there are two outputs, OCNA and OCNB. Uh, so these outputs are like coming from the OCRNA and compared with the counter. This counter is compared with OCRA, will get the output OCNA. This counter compared with OCRNB will give you the OCNB. So that is the basic idea of this one. So with these two registers, we'll configure how the timer will run. This is for comparing the outputs, and this is the counter. So what we can do with this? Let's see how the patterns go here. These are the different modes in which the timer can work. So what is the normal mode? So in normal mode, you have uh, let's before that we have to see the registers, right? So it's TCCRA, this control register, has certain bits, COM bits and WGM bits. These COM bits are for the comparison mode uh, definition. Like we have to set the comparison. So there are multiple comparison modes that are there. To set that, we use this. This is for output A, and this is for output B. And this wave generation mode bits are for configuring the type of wave that is generated. Okay. So if you see, these are the different configuration of the compare match output mode you can configure. Normal operation, toggle on compare, clear on compare, set on compare. These are the output bits that you have. Okay. Mm, okay. Let's see. B will be same as A, but instead of output A, it will change the output B. Then wave generation. So what are the different types of waves that we can generate? So one is normal mode, and PWM is there, pulse width modulation, and CT is compare match thing, and there is a fast PWM mode. So these are the different. So this is space correct PWM, fast PWM, normal, and compare match. So if you see now here, these are the four modes that are given here. So in normal mode, what happens is basically the counter TCNT increases as the wave like each clock cycle, it will increase. And after going to 0xFF, which is the 8-bit limit. So since this is an 8-bit counter, this is the 8-bit limit, right? It will go there and come back to 0. That's how this will happen. So when this overflow happens, there is another flag TOV2. This overflow will be turned on, so that can be done. Okay. And then, yeah, in timer compare match mode, what happens is we can set another register, this compare register, its value, and if this mode is set to this, so what does this mean? Any idea? So WGM2 is the wave generation mode bits for the timer 2. This 2 is to 0 represents the range of bits is equal to 2. So the range of bits in the sense, then we saw the uh, PCRA bits. Yeah. So we WGM 2, 1 and 0. These bits is what it is referring to. So it might be very complex notation if you see this timer register names. But once you understand the different parts of the timer, this will be easy to. Okay. And yeah. So there is also these set of registers that are there, TCCB, this one. There are two set of configuration control registers that are there, right? So there is one bit from wave generation mode is present here in this B register, and these CS registers are used to select the clock source. So there are different prescalers available for the clock source. If you see this, prescalers are like, um, for the this clock, this prescaler by 8 will only pick once for every 8 ticks from the original clock. So this will reduce the number of clock ticks by 8. So that's what happens. So the counter will be slowed down, and this will even slow down the counter according to the clock frequency. And these three bits, CS2, these three bits will help us select the particular clock source. So understanding this timers will be quite difficult, but if we try some code, it will get better. Okay. Mm, okay. Let me an example. I hope my screen is visible now. So now, uh, let me explain this code, how it is going to work, right? So basically, what we are going to do is, we are making use of the normal mode in the timer. We are not nothing doing nothing special in this timer too. So whenever this overflow happens, we are going to increase the number of overflows to change the like state of the cell basically. Okay. So what we are going to do is, first of all, we are setting these two pins. So what this is something called as a logic analyzer. So when you add this, it will generate a file which will have the waveform of the voltage levels that's happened there. Okay. Let me explain what this code is. So initially we are setting the pin mode for these two pins, D4 and 5, and then, so what is this BB? Any idea? So this is kind of a shorthand for writing this. Instead of writing one, sorry, one, two, DD5, we can write BB because if you see what it expands to, the same thing. Sorry, this. That's what it does. Basically, BB expands to the same thing. So you can, so which means bit value. That's what it is. So you can write, instead of writing it that way, you can write this way, like a functional form. So we are setting that, and then what is this TCRB2? That's where we can set the clock source. So all the CS pins are there in TCCRB, right? Um, Number two is the description TCCRB. So these three pins we have to set, right? So if you see, so for no clock source, we have to have everything as zero. Sorry. But we need a hack clock source, right? For the counter. So we have to set this with no pre-scaling, the actual clock. So to do that, we have to set this bit to 1. That's what we are setting here. And this is for enabling this overflow interrupt. So in normal mode of operation, you can see this mode of operation. What happens whenever the counter overflows, this flag will be triggered, and that will make something to happen. So that is what this interrupt is. It will cause this timer 2 overflow to happen. Okay. But to enable that interrupt, what you have to do? To enable that interrupt, is still mask. This is how we enable different interrupts. So to enable the timer overflow interrupt, we have to turn on this bit. There are other forms of interrupts also available. So that comes in compare match. That compare match we'll see in the CPC. Okay. So if overflow happens, if you want to enable that interrupt, this is the register and you have to set this bit. That's what we are setting. And this is for enabling the interrupts globally. This function ACI will enable all the global interrupts. And this in this interrupt, what we are doing, we are creating a interrupt service routine. So this is how you create an interrupt service routine for a particular overflow or like for a particular interrupt. Yeah. So this ISR will expand that to a particular interrupt routine, interrupt service routine. You have to pass the interrupt service name. Yeah. So with this, we can have this task that's happening. So what is the default clock frequency? Default clock frequency is 16,000 megahertz, right? Which means, so you have a 8-bit counter. So with that clock frequency, Um, let's see, 16 megahertz corresponds to 16 times uh, this, right? 16 into 10 power 6 is mega. So this many number of times it will happen. So you have a 8-bit counter, which means how many overflows will happen. This is the number of overflows that happen. Okay. So with that, sorry. So it starts from 0 to 8-bit, and which is 56 values. So which is 6250. Okay. Yeah. So this is the number we want. We are doing no pre-scaling now. So which means after this many number of times overflows, our 1 second would have elapsed. So if you run this, after 1 second we are toggling the port key, which is the LED, but we are actually toggling this whenever the timer goes off. So the timer counts complete. So that's what we are doing. And yeah, so let's see this. Stop this. We have this logic.c. This these are the signals that we have captured. Okay, so this happens in 1 second. This would have gone on and off that many number of times. That's the idea, and in 1 second, this will go on. See this one. In 1 second, that will turn on. That's how we come to this. You can see this there. In 1 second, this LED will turn on because we have counted that many number of times. So the overflow happens after that many number of counts, and after that many number of overflows, it will take 1 second. That's how we can measure this LED is blinking at this rate of so let's run this for some 2, 3, 4, 5. This will generate the this. So to view this VCD file, you need to have this extension also installed. So this extension is called wire wave trace. This this extension is installed. Yeah, so let's see that, right? After every second, the timer is going on and on. So what we are doing is every overflow happens in that many numbers of time, and we are doing toggling this one. So signal, this signal here is D1. Yeah. So this D1 goes on and off every time the timer goes on and off. That interrupt service routine happens at these points. But after counting that many interrupts itself, we are changing this LED. And that's how we toggle that LED at a certain interval using timers. They can generate these kind of waveforms. Right? This is very normal. So there are also other modes that we can use. For example, we have used this one, right? Uh, okay. So now as you, we have to do a step rescaling. Okay. So without rescaling, the clock will be running at its own pace. We want to reduce the number of overflow counts also. So this is actually many times it's counting and then doing something to turn off that LED, right? We want to reduce that number. So we want the number of things to happen less. This overflow to happen less number of times. So there are other ways to do it. So what we can do is in this we can operate in this clear timer comparison mode where instead of triggering this at this interval, you can actually trigger at certain other intervals also. You can set the OCR2A register to a certain value and it will work accordingly. Like the frequency of this will be with that. So it won't go to the top. That's the advantage of this mode. Okay, so if you want to set this to this mode, we can try something. For example, so our so this is the clock frequency. Assume we are using a what is the highest prescaler we have 1024 prescaler, right? And so if we are using this one, they are using 1024 prescaler. This many times the timer goes on. Okay. Uh, this many times the timer goes off in 1 second. So that's what we need, right? So, but if you want to reduce this, what we can do? Uh, so instead of reducing this one, yeah, okay. So what is this 125? So this 125 is the value that we can set to the timer's counter. How many times it counts in 1 second. So with this idea, we can set this timer counter instead of going to 2FF, which is 256, we can make it total 125. And we can set the prescaler to 1024, which means the clock's actual frequency will be reduced. So after 125 overflows, you can measure 1 second. The advantage of using the prescaler is less number of overflow will happen, and you can use this compare match mode to do this. So interrupt flag, right? So we have to use these things. How do we set that? Um, okay. So to operate this mode, first we have to set this one, the wave generation mode, which is present in PCCA. Here uh, we need set on compare match. So which means we need set on compare match. This we actually don't want, right? We just need the overflow. So first we have to set the prescaler using this. So set the 1024 prescaler. We have to set everything to one. So we will do that. Use 0, 1, everything to 1, and everything to 1. So which means 1024 prescaling, right? And instead of timer overflow interrupt, now we are going to use compare match interrupt. So what are the other interrupts that we had? This one. Purchase OC IA through a interrupt enable. So compare match, whenever the compare match is happening, it will enable that. So you have to set this bit to 1 instead of that. So I am taking that bit and here, enabling timer to output compare interrupt. For the also, what are the other things that we have to do? First, we have to set the wave generation bits. So here, in this wave generation, if you see, we need uh, this is normal mode. Yeah, compare match output mode. This one, compare output. This is what we need. Yeah. So we need. We are not taking the output anyway, since we are using only the interrupts. We don't worry about the outputs, so we don't need to set this actually. Uh, yeah, this value we have to set compare match value. These two bits we should set. Uh, sorry, no, we have to set this one OCR2A. This OCR2A will set the compare. We will have to set the compare value there. So which is in this case 125, right? So we have to take this register and set that value. Compare. To 125. Let's set this to 125 overflows. Instead of time up to overflow vector, now we have to use the other interrupt, which is time one compare, time two compare A. When this match happens, we have to enable this interrupt. It's the interrupt we need to set. Rescaling done, compare match done, compare match A done. Let's try. center of the planet is set. Oh, okay. We will set the wave generation matrix, right? So wave generation matrix to this one. Yeah. Uh, we have to set it to this wave generation matrix. Yeah. For CTC, we have to set this to this value to two, which means WGA. So this to set PCC R2A. Okay. We have to set that. This is okay, compare this one. Set. Yeah. CRA. So set. Timer mask is also set. Seems So we are actually having this signal coming in. Okay, okay, okay. Seems the LED is also blinking, but at a faster rate than we expected. There is something wrong with the calculations. Yeah, this LED is blinking in a faster rate. Uh, we calculate, so the code is working fine. So pre-scaling. Oh, oops, pre-scaling was the issue. This should be. Yep. Now this is cool. So now if we save this and see this, so D1 is the counter. Now you can see the counter itself is overflowing. That compare match is happening after some 8 millisecond only. So that with less number of times this overflow, like after 125 times, you can see it is happening in 1 second here. So this around 1 second this is happening. You can see that, right? Is it clear? Uh, I think there is one more bit like times it is going. Uh, okay. So here we can say since this overflow is starting from 25th overflow might be the, so the first overflow happens here. There is one around, so we start around 8 milliseconds, right? So it happens around 8 milliseconds. Spree scaling happens. Then we are setting, so whenever the counter reaches 125, that overflow happens. So that was the idea. So overflow, and whenever that overflow happens, uh, we toggle this thing. So first overflow, second overflow, third overflow, and it goes on like that. And around here, during the 125th overflow, we are changing this value. Okay, that 8 millisecond. I think we should turn on here itself. So let's change the 124. When it becomes 124, since I think we are starting from 0, the n overflow is starting from 0, right? That's why it's happening. So 0 to 124 will be the 25th overflow. During the first overflow, uh, this, yeah, now you can see the number of samples is also low because the trigger is happening at a very slow pace. Let's see this signals. Yeah, yeah, exactly. Now it is happening at 1 second. The 124th overflow. there. So this with this we can actually measure the 1 second very accurately. Okay, see this right here. So yeah, okay. So this might be very hard to understand all these resistors and things. So you might some need some time to develop this. Okay. I think that we can end today's session if you don't want to ask anything. Okay, thank you.